Two fabulous speakers, our best speaker of the night. Oh, wow. Big claims. You can decide at the end of the night. Please welcome Dr. James Davenport, research scientist at the University of Washington.
Good evening, Astronomy on Tap, Seattle's premier tent-based science outreach activity. Okay. Astronomers hate this one weird trick. 7 tips to reduce your gray matter fat. Insert other clickbait titles. You've seen them, I've seen them. We're going to talk about them. And because I feel like I'm here with 100 of my closest friends, I want to give this talk on slightly a personal note. This is something that I haven't really talked about before, so come along with me on this journey. Be a little forgiving as I kind of explore this thing that's been sort of bothering me, and I want to get it off my chest, and I want to talk to you about this. But before we dive in, I want to set some ground rules for what I'm going to say and what I'm not going to say. And the first thing I want to say is thank you for coming out. Thank you for supporting science, local scientists, local business, local beer, local vegan hot dogs. And thank you for supporting knowledge and truth in a time when we really need more of that. Thank you. Give yourself a round of applause for that. Okay, good. Cheesy audience interaction check. Next. Okay, the first thing I want to say is, am I over this way? Okay, there we go. The first thing I want to say is, I am a huge fan of science. I love science, right? There's a reason that I do this for a living, and it's not the pay, and it's not the glamorous office, though UW is a lovely campus and you should all visit. But I fucking love science, right? It's awesome. And I love every time I see in the news cool headlines, amazing graphs. I love that graphs have become part of our narrative and part of our news media. It's an exciting time to be a fan of science, to be part of the sort of cultural movement that appreciates knowledge and the search for truth. Thumbs up, science. Okay, so first, I love science just like you. I'm a fan of science. The second thing, which I think is actually just restating the first thing, is that when you're a scientist or when you're a fan of science, you love failure. You love being wrong. Being wrong is just nature telling you that, nope, try again. Come up with a better idea, a better explanation for how the universe is working. So if you love science, you have to love the struggle and you have to love truth. Okay, truth. And that's what this talk is about. It's about rooting out the BS and discovering the truth and appreciating and celebrating the truth. Being wrong is okay. I'm going to talk about clickbait articles and headlines that didn't turn out to be true or were over-exaggerated or pictures that were like, oh, that was photoshopped. And let me just say, I have shared and retweeted a bunch of these myself. So we're not here to dunk on people who are just enthusiastic. We're here to help get everybody on team truth, team root out the BS. So being wrong is okay. Let's move forward from there. So, with those ground rules in place, come with me as we talk about clickbait, misunderstandings, and maybe even some outright lies. All right, the first example I want to talk about is one that started many years ago, something like almost 20 years ago, which is this so-called the Mars hoax. I'm sure people have seen this in their inbox with like forward, 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 go outside and see Mars. It's going to be the size of a ham sandwich in the sky, right? I've seen this email repeatedly over the years. This is called the Mars hoax. It even has its own Wikipedia page called Mars_hoax. And it tends to crop up every August, sometime in late August, usually August 25th or 27th, something like that. And the claim is that go outside because Mars is going to be so big in the sky that it'll be giant and it'll be awe-inspiring. It'll be as big as the moon or as big as, again, a ham sandwich or something. I don't know. It'll be huge. It'll be spectacular. It'll be the last time in 40,000 years that you'll see it. And you got to go outside. And then you go outside and you're like, okay, I don't see anything. These people are idiots, right? And then you're like disappointed, and you're like, science is stupid. There's a reason I didn't do this in college. And you move on, and like little by little, we chip away at your interest and your excitement and your enthusiasm and your belief and your trust in science as an institution. Okay, the funny thing about this hoax is that it was based largely on the truth. Is that about 20 years ago, there was a time when Mars was the closest it had been in like 40,000 years. It was slightly closer than it usually is, which made no perceptible difference whatsoever. Mars just looked like a dot, right? You go outside, it's like, yep, It's that one? And that was Mars at its closest opposition. And it was cool, and like Hubble, I think actually even took this photo. The Hubble Space Telescope actually took this photo at that point because it was slightly closer. I think it was cool. But this has morphed and recurred because it's so spectacular and ridiculous. Okay. Here's another great one that I see a lot. Anytime there's an eclipse, any kind of eclipse really, you see this thing floating around Reddit and Twitter. Like, oh my God, the astronauts leaned out the window and took this picture of space. Wow. Right, and it's awesome, right? Look, that's just objectively awesome looking. There's like the Milky Way, and there's a shadow, and there's contrasts and colors. And this is somebody's work from art website, DeviantArt. This is somebody's Photoshop where they were trying to show off like cool stuff. This was not meant to deceive you. It was meant to be like, hey, look at my Photoshop skills. And instead, it's been co-opted into this hoax about like, this is amazing picture has only been seen by astronauts eating ham sandwiches once in 40,000 years. And it's, of course, it's nonsense, right? This is not what an eclipse from space looks like, and you wouldn't see the Milky Way. And but the enthusiasm is good, right? That's the point. The people aren't sharing this because they're trying to get you to buy something. They're sharing it because space is cool and science is cool. And I've hit like on this before and then be like, ah, damn it, this is the Photoshop one, right? Eclipse from space. Okay, the third one that I want to talk about right here is the super blood wolf coyote moon thing, right? Like, we did have some amazing eclipses, some amazing, this was from space.com, but like some amazing eclipses. This is all good. Well, I'm happy here. I don't love the title. I don't know what a blood wolf moon is or what makes it super, but like, I'm fine. Go outside, watch the eclipse, it's cool. It's amazing, take a picture, it's great. This is fine. This is a problem. This is Rio de Janeiro, plus, I don't know, like a Ridley Scott movie, right? This is problematic, because you go outside and you're just like mad disappointed, like, what? Right, you can go, I mean, this should tell you this is a problem because it's even on Snopes, right? There are BS websites, Snopes.com, the super moon nonsense. This is a problem. Okay, the point of part one of this talk is science communication is important. We gotta communicate what's true. This is a great headline from ironically, I fucking love science. They retweeted, this was yesterday, I took this screenshot, so it's 15 minutes plus 24 hours. Millions of Americans think chocolate milk comes from brown cows. Come on, what? No, that's not true. Right? I don't think so. The survey that they link to says 7% of adults in America think chocolate milk, this is not astronomy for all those playing along, this is just milk. 7% of adults in America think that cows produce chocolate milk. And what's funny about it is also this survey was kind of garbage. Like, if you go back and look at the survey, like they did do a survey, but the survey is not rigorous. So the whole thing is just nonsense. And it bounces back and forth. And what I love about this is that the guy is like offering the cow, there's 2 straws. The 2 straws slays me. But then he's like, here you go, cow. Okay, but the point, if there is a point, the point is that science communication is important. And chocolate milk is delicious. Let's talk about some real science. Okay, so that's popular culture stuff. Okay, this is the stuff that pops up in your news feed, in your email. This is what I work on. I've written a paper on this star. I've worked with the lead author of this study before. This is a really amazing, true, amazing detection of what's called Boyajian Star, named after Tabitha Boyajian, a professor who discovered this amazing object. And here's the deal. This is why we all went, whoa, is that it did this. It had these wiggly lines. And you know, to scientists, that's a huge deal, wiggly lines. And because the shape of these lines were totally unexpected. Something passed in front of this star to make it go dim for a day or two, and it had a really weird profile, and we don't really know what it is. And that's the God's honest truth. We don't really know what, it's probably dust, or like a comet, or like a bunch of comets or something. That's not that exciting. Nobody's going wow out there. Okay, so the Atlantic picked this up because it's kind of cool. It's a really unusual discovery. The most mysterious star in our galaxy. All right, that's fine. That's fine. I don't have any problem with that. Astronomers have spotted a strange object. Yeah, it's fine. Scientists study extraterrestrial civilizations are scrambling to get a look. I get a little worried. We're okay. It's fine. It's fine. It's the Atlantic. It's a good publication. You should subscribe or whatever. Here's a funny outfit called the Washington Post. The flickers are consistent with an alien megastructure like this artist concept of like Halo or something. Is it flickering because of aliens? Show more. It says no. It should say no. Okay, this gets better. This is the fine folks at Discovery. Again, we're not trying to dunk here. We're just trying to point out interesting facts. Has Kepler, the space telescope that discovered this, has Kepler discovered an alien megastructure? No. I love this one because the artist's rendition is so pointless. Like, it looks like Firefly. Why did they cancel it? Okay, here's one more on Boyajian Star. Have aliens built huge structures around Boyajian Star? Probably not. But alternative explanations are hard to come by. This is true. Here's another good artist rendition. It looks like a bunch of iPhone 8s centered around a campfire, which is funny. And here's the really funny part about this one. Scientific American is a pretty reputable publication. Here's the funny thing about this one. This guy, Jason Wright, is a professor of astronomy at Penn State University, is an absolutely brilliant scientist who I've worked with. And this is a former graduate student of his, Kimberly Cartier. They are the real deal. And this is the problem. You gotta write this, or at least the editors think you gotta write this headline to get people to click to read the article. The article is completely sensible, right? But like the headline is ridiculous. And I'm making fun of Jason because he's smart and I love him. But we do look for weird stuff, right? We do look for weird exotic patterns. This is an illustration that I drew of exotic patterns we might see in data that could be indicative of aliens. Jason himself actually works on the honest-to-God search for extraterrestrial intelligence. It's a fascinating topic that's finally getting some traction and not being just laughed at. I'm hoping to come back and, yeah, thank you, right? It's awesome. Like, we ought to look. I want to believe, and we ought to look, right? So there is real science here, but oh golly, we need to be careful about reporting them, right? These searches and these finds, we gotta be really careful. We have an obligation as scientists to be really careful. And I worry that we're not. But, ominous logo hiding off the side of the screen. But we are faced with an even bigger challenge. A challenger who has a lot bigger machinery behind them that we are going to have a hard time beating. And that is the social media science fan accounts. Okay, so I'm not trying to pick on I Fucking Love Science because they do great work, occasionally get it wrong, but they actually do really care about science. I don't want to pick on them, but I'm going to pick on some other people here. Okay, here's an account called @physics-astronomy or @orgphysics. They got a really cool domain name. Here's a picture they posted September 6th. View of Hurricane Dorian from the coast of Florida. Spoiler, no it ain't. And like, you know, hurricanes are a big deal. We don't get a lot of them here, but they're a big deal. They kill people. They're not really that funny. And if you saw this on the TV and you went outside and freaked out, like, oh, we got to pack up and run because I recognize this coastline. We got to run. This is not great. I don't like this. This is unethical, I think I would categorize this as. And they have 110,000 Twitter followers. This post had 100,000 retweets. That's a huge impact for something that is just garbage, just a lie. Here's another one from @InterestingSci1. I mean, to their credit, they don't try to explain what it is. They just say, wow. But like, this is like a baking experiment gone wrong in, what is this, Toronto or something? Shout out Toronto. Yeah, this is Tim Hortons. They have 143,000 followers. This has 15,000 views. It is, I don't know what, I mean, like, it's fine if it's art. It's fine if it's art. It's cool, like, it's engaging to your eyeballs, but like, it ain't science. And it's not Science and Nature, the account title. You know, I worry about this. This is what's causing me worry. How do we fight back against this? Here's one more. Okay, at Zone Physics, which is sweet Einstein logo and a cool banner. And oh, they got a great URL, physics-astronomy.org. That's cool. That's a great URL. I wish I had that domain. And 800, almost 850, better part of 1 million followers, okay? And they posted, this is yesterday, November 20th, 2019. Yesterday morning when I grabbed this, it had 250 retweets. It's since grown. Pluto has been reclassified as a planet. Rejoice. No, it hasn't. That is a lie. Not only that, if you click on their silly website and you go to the article that's linked, it's a link to an April Fool's article. What do we do about this? Okay, yeah, physics, yeah, whatever. Here we go. They're a big deal. They got lots of followers. This is a huge impact for nonsense. This is going to cause people a lot of confusion about what we do. That like upsets me a little bit. Not like, damn it, you got to get it right, or like you should know better, but like the due diligence. Where is the celebration of truth? You got it wrong. I'm not worried about that. I'm worried about, oops, we screwed up. Where's that post? Where's the integrity to say, we messed it up? It's okay to get it wrong. I get it wrong all the time. At 850,000 followers, there are only 2 astronomers in the world with more Twitter followers than that. One is Dr. Neil deGrasse Tyson in New York, TV celebrity, right? The other is Dr. Brian May, also known as the guy from Queen, right? Like, he was only in one of the biggest bands of all time, and he's only got 1 million followers. So go follow Brian May, huh? And then this account slides in above Phil Plait, the bad astronomer, who is one of the biggest deals in astronomy communication. If you're not following Phil Plait, man, get on your phone right now. Ignore me. I got 2,000 followers. Ignore me. Go follow Phil Plait. He's the real deal. These people are crushing him. Like, this is concerning. Why? Why does this page exist? Here's your answer. This page has nothing to do with physics and astronomy, of course. It has to do with affordable islands and a man turning an airplane into a house, which actually does sound really cool. And look what the deepest hole in the planet has. And this yacht. Right? These are ads. I think this is self-explanatory. I think this you can understand what I'm saying here. This is a machine to get you to click on things, to get your eyeballs on things, to get you to engage with things so they make a few pennies. And they do that 1 million times a day. Whew! That's depressing. Where's my beer? Dramatic interlude. So, what can we do about it? And I don't mean just like, what can we, the noble astronomers, I mean like you, what can we do about this? Because the fact that you're here gives me a lot of hope. The fact that this is the 56th event for Astronomy on Tap Seattle, shout out Astronomy on Tap Seattle, 56th event. Amazing. It's freezing and this place is still full of people. It's not actually freezing, thank you, that's true. I was wrong. Thank you. Keep them honest. What can we do about this? Because I don't want you to be like, man, the internet sucks. Because the internet doesn't suck. The internet is why we're all here. The internet is how you found out about this event, likely. The internet is how I reach people every day and communicate science. The internet's a great thing. This is like a cultural problem that we can address. I want to end this on a hopeful note. So I have 3 action items, 3 things that we in this room need to do. Number 1, we need to communicate about science. We as scientists need to communicate as science. There's a great little blog post by Professor Michelle Frankel from Bryn Mawr College, and she ends it by saying, if we don't tell them what we do, the pseudoscientists will. They will fill that vacuum with nonsense. Now, she's a chemist, and so people are worried about putting chemicals on their hair and vaccines and stuff, like real problems. Vaccines are good. Vaccines they're a good thing, and chemists worry a lot about bad reputations. Yeah, if we don't tell them what we do, the pseudoscientists will. That's a real threat. So, to the scientists and the science-focused people in this room, tell them what you do so that nobody thinks these things. So that nobody thinks that chocolate cows make the super blood moon, or whatever. We gotta tell them about the science. We gotta spread truth. It's important. Number 2, you, more broadly the people in this tent, can help share and intervene. One of the only ways that we can beat fake news, I hate that term. One of the ways we can so-called beat this kind of phenomenon is by intervening and telling people, actually that was garbage. And it feels so helpless in the moment when you have these tiny interactions, when you're butting heads with your great aunt or whatever on Facebook. But like, look, 250 retweets. We gotta try. We gotta try to intervene and tell people that wasn't true. There is research. I should have put a citation here. There is research that shows that by making these interventions, by telling people that like, hey, that was not a really reputable source that you linked to that one time, maybe you should try. People actually do tend to get a little better. There is some hope that by elevating the discourse of people about science and about truth more broadly, that we might hope to center around something in this world that is true again. I think that's an important thing to strive for, and you all can help. It matters when you subscribe to somebody like Phil Plait and retweet the things that are cool about science, and it matters when somebody retweets the super blood moon over Rio de Janeiro with a cow jumping over it, that you say, that looks like Photoshop to me, I don't think that's real. Those things help. And third, and I think this is a more subtle point, but because we're in Seattle, I think it's worth standing up here and trying to make at least. We need the help of technology and technology companies with this problem. Now, I'm not the only one saying this by any stretch of the imagination. Finding spam and finding falsehoods and fake news is a huge deal right now, and a lot of really smart people are working on it. I took this screenshot of the Google Optimized Resource Hub, which is just like a documentation hub for how to get people to like look at your website and click your links. This is a really useful resource for developers who are trying to make websites that are pleasant to look at and great, because they want eyeballs. Because the entire economy of the internet is based around eyeballs. We need other solutions besides just eyeball time equals dollars equals the only thing that matters on the internet. We need tools that help us optimize for things besides just eyeball time. We need tools that help us figure out what's the most efficient way to get knowledge across. What's the most efficient way to identify bad actors who are spreading misinformation and intervening when people are trying to share that content, saying, just so you know, that's BS. How do we get these tools? I am not a programmer by trade. Some people in this room probably are. This is something important that matters to us, that matters to scientists, that we need tools and we want tools to help build partnerships that will reward people who are creating science and science knowledge. So Also, Dr. Jesse Christensen, another amazing astronomer. Vlogbrothers, I think the best channel on YouTube. Yeah, right? Shout out Vlogbrothers. Hank and John, there you go. There's the AOT bump. We already do this to an extent, right? These platforms verify or put fancy check marks or stars next to people's names. Why not little brains? Why, I don't know, this is like a cute idea. Why not? These are good sources of reputable truth and knowledge. Why not reward this by helping draw the reader to these kinds of sources? This is one trivial example. And going back to number 2, technology companies and advertising companies will care if we all care. If we are subscribing to scientists and broadcasting that message of truth, then they will pay attention. And if we just succumb to the garbage, that is floating around on the internet, then they will help continue optimizing for garbage. So subscribe to your local homegrown scientists and to your truth. All right, and in conclusion, again, these 3 action items. We need to do science outreach. We need help from everyone to spread truth and to identify falsehoods. And we need the help of technology companies. And with that, I will thank you all for coming out again tonight. And we have time for questions, but I am going to drink the rest of my beer. That's a good question. The question was, what clickbait have I fallen victim to that turned out not to be true? That's a really good question. There's a lot of well, first off, there's a lot of borderline clickbaity headlines that we put in our own research articles. People put kind of falsehoods or very misleading titles occasionally. That I often fall victim to and read the article, but that's probably not a bad thing. Oh man, I've fallen victim to a bunch of eclipse photos, I will admit. It's cloudy here and we don't get very good eclipses. And I don't know, I've never seen a full eclipse by eye. I fall victim to those. And other cool aurora photos. I have been caught retweeting some fake ones as well. They just look so cool. The art is so good. Yeah. Oh, a really good question. Actually a good question. How do we know that Tabby star or Boyajian star is not an alien megastructure? The short answer is all the available information right now points to it being dust. Some kind of thick, grainy, opaque dust. It changes in color slightly when it gets dimmer, and that is consistent with dust. The other reason we don't strongly suspect aliens is that incredible claims require incredible evidence. And right now, the simplest assumption that we can explain the data with would be dust. Aliens would be very, very complicated. And this is not obviously physically impossible. So when you start talking about trying to detect aliens, you want to try to detect things that are otherwise utterly impossible. And dust is very possible. There's plenty of dust in the universe. Yeah, how would they even build this megastructure? Super good idea. Don't know how you would build a giant halo thing orbiting around a star. A Dyson Sphere would be the idea. Jason Wright actually is one of the people who have shown that we don't see any strong evidence for a Dyson Sphere. So if you were to build a big structure around a star, like a Dyson Sphere or a bunch of rings or a megastructure, you would absorb a lot of sunlight. And that means your structure would heat up, and your structure would then radiate warmth, infrared heat, like these lovely lamps above us. They would radiate warmth. And we have telescopes that look for infrared light. The WISE telescope famously surveyed the whole sky about a few hundred times over the past decade in the infrared. And so Jason Wright and his team have shown that there are no stars that show anomalously high infrared glows. So you don't see any weird stars that are oddly faint but have huge infrared brightness, which would be explained by reheating from a Dyson Sphere. That's the best evidence for that. Yeah, back there, shout it out.
Other than this, what are you doing to make your research more accessible?
Ooh, what a great question. Thank you. I didn't even plant this one. Other than this, what am I doing to make my research more accessible? Well, you can go check out my YouTube channel, LOL. A bunch of people at the UW, including myself, try to put ourselves both on social media like YouTube and Twitter, and we try to shout out each other's work, try to tweet about it, try to post about it. I try to make videos. There are other people who try to make videos that distill the work into an everyday, understandable language. Right? One thing that has been shown time and again to really work is just cutting out jargon. It's just getting used to talking about what you're doing in a everyday kind of context. And so trying to put myself into a context where I'm doing that every day is important. So shameless plug for my own social media accounts, but also for the people who are here and run AOT. One example of how I try to get my research out is I come to and I support events like this. Yeah. Woo! Yes.
Hi. I really appreciate that you are saying that it's okay to be wrong, because I fully support that. Could you speak to a time where you've been wrong in your own research and how you've rectified that?
Ooh, good. Put me on the spot. The question was, she appreciates that I said it's okay to be wrong, so put my money where my mouth is. What's one time that I was wrong in my research? Well, let's see. There's been plenty of times when I've speculated out of hand. So one time that I made an inaccurate prediction. I published a paper 7 or 8 years ago about two stars, a binary set of stars that they're orbiting each other, they're caught in each other's gravity, and it's a very short period. They rotate around each other, they orbit around each other every 8 hours or something. It's incredibly fast. These two stars are locked in this like cosmic death spiral. And we had a bunch of observations over several years of these stars, and we measured how fast are they spinning around each other. And I really pushed that data. Like I really strained to try to see if that shift, if those stars were accelerating, if they were spinning in faster and faster and faster, which would indicate that they're about to collide. And this causes like what we call a luminous red nova or like some kind of stellar merger. They're really cool and very rare. And I was like, ooh, God, maybe I found one. And so I wanted it. I was a young graduate student. I wanted to find this thing. You can go and find this paper. And there's a very suggestive plot that does not have very good error bars. Where I show like if you take this side of the data, we look for what the orbital period is. And then we take this side of the data, it looks like a line. And that suggests that it's in-spiraling, and this is going to be really amazing. And then we came back like a year later with a better telescope. We sat on this star for like 6 nights, and it's not doing that. And I didn't publish that, right? Like there's me owning my shame, my wrongness. I was a young student who needs a job and who's trying to win grant money, and it's not exciting to publish like, I was wrong. Like that's not an exciting paper. I got another paper that I'm working on that's cooler. Don't ignore that. Don't worry about that paper. I got another one coming up. Right? And like there's these games we play because you need attention, because the eyeball economy isn't just the internet, it's about jobs, it's about grant funding. But there you go. There's the honest answer. Good, this has been healthy. Yeah. How do we change the incentive structure in academia? Yeah, I have one thought. I'm not sure if it's super helpful. I think, so a lot of what people like me, so I'm a research scientist, which means I don't have a tenure track job, which means I'm not paid by the state. I'm paid by grant money that the feds competitively allocate. So I spend a ton of my time writing grants, which is like fine and rewarding, but is also super horrible and like dehumanizing and sucks up a ton of time. It takes like, you got like a 1 in 10 chance of winning one of these grants. And it might support you for a couple of years. So you gotta spend you can do the quick math and figure, well, it takes me a couple weeks to write a grant, and I got a 1 in 10 chance of getting it, and it's gonna support me for 2 years. I have to spend like half my time doing this, just to play the game. That sucks. Just do a lottery. And it sounds tongue-in-cheek because I'm lazy and I don't want to write grants, but it's also not clear that past a certain point we can differentiate what's going to be the best science, the most transformative, the most spectacular, or the most important. These grants and these dollars are precious and limited. We spend so little money on NASA and on the National Science Foundation and the National Institute for Health that you convene a committee of like-minded people and people with PhDs and very serious scientists to pour over 20 or 30 of these grants to pick 1 or 2. And how do you pick? They're all good, or at least half of them are great. How do you pick? I don't know. It's not clear that we always pick the best thing, and so some people get lucky because of their reputation, and some people are doing the cool, hot new thing, And some people are out in the Never Never Land trying something cool, but nobody's heard of them, and they don't get lucky. I don't know. I think one possibility is making some fraction of the money equitably available to all. That to me seems like one possibility. It's a radical change. We take the idea of peer review and judgment very seriously in academia, and we're going to be really reticent to get rid of that. But it's possible. Anything's possible. All right. Thank you all. Tip your scientists.
I'd like to introduce our second speaker of the night, who'll be telling us an abridged history of the universe. Please welcome please welcome. Sorry, technical difficulty. We're making sure our live stream is on. Are we ready to go? Okay. A moment to build the tension so you can be really excited about our next speaker. Woo! I guess in the meantime, I can announce that we will not be having an Astronomy on Tap in December due to the pervasive darkness and cold, and also traveling to see our families. But we will be back the fourth Wednesday of January 2020, starting a new decade, Astronomy on Tap number 57. So we hope that we'll see you there. For your patience, we are a ragtag team of UW graduate students who put on this event, and sometimes things don't work out quite as quickly as we hope that they will. But shout out to our videographer for keeping our live stream going every month. I'd love to introduce our next speaker of the night, a University of Washington astronomy professor, Professor Matt McQuinn.
Woo! Thank you. Since my colleague Jim basically didn't cover any astronomy, I've decided I had to pack a huge amount into this talk. And so in the next 15 minutes, I'm going to summarize everything we know about the universe. Okay, and I titled this "A Universe is Life," and you'll see why. But so before we get started, before I start, before we discuss the life of our universe, there are a few lessons that we have to discuss. And so the first is that space likes to move. And so what do I mean by space likes to move? That this means that space doesn't like to be static. It either likes to expand or contract. And there's nothing so mysterious about this. And so when we look out at other galaxies, almost all other galaxies are moving away from us, and the further we look, the faster they're moving. And this is the expansion of space, and it's totally correct to think of those galaxies as moving away from us. That's what expansion of space is. It only gets tricky when they're moving at what looks like faster than the speed of light. Then that's when you need you need to think about it in a different way. But so the expansion of space is just things are either moving away from us and or they're coming towards us. So nothing mysterious there. And also I should say that there's also no center for the universe. So if I were in another galaxy and I were looking at other galaxies, I would also see all of those galaxies moving away from us. Okay, that's lesson 1. Lesson 2. So space is expanding. So that means that if we go back in time, things were denser. Everything was closer together. All galaxies were closer together. If I took the air in this room and I compressed it, it will heat up. In the same way that if I blow air out of my mouth, it will expand and it will cool down. And where I put my hand, it's going to be cooler the further I put my hand away from my mouth. So the process in reverse, if I took the air and I compressed it, it will heat up. And it'll heat up more and more as I compress it more and more. And eventually what happens in our universe is things get so hot that they start hitting each other and producing other particles. They might produce electrons. Or if I get them fast enough, they might start producing particles that we've never seen in the lab. And so the early universe is way different than things we're used to, because the things can get really hot, and we can get and this means that we can get an exotic zoo of particles that we've never seen. Okay, and lesson 3. And after Jim's talk, I acknowledge that my title is a little bit clickbaitable. And I please do not quote me, but so light travel equals time travel. And what I mean by that is that what is shown here. No, I have a laser pointer. Stay back. What I mean, so this is the Hubble Ultra Deep Field, and so this is the deepest image we have of the sky. Almost everything that you see in this, every source is a galaxy. The size of this is about 100th the size of the moon. The size of the moon, if I put my arm at arm's length, my thumb at an arm's length, the size of the moon is roughly the angular size of my thumb. This is 100th the size of that. You look at it, and you see all of these damn galaxies. Like, there are a lot of galaxies. There are a lot more galaxies in the universe than there are stars in our galaxy. There are 100 billion stars in our galaxy. In the observable universe, there are more like 1 trillion galaxies. All of these galaxies, like the closest galaxies, which are the biggest galaxies, are hundreds of millions of light years away. That means it's taken light hundreds of millions of years to travel. So we're looking back in time. And actually there are, in this image, the furthest galaxies we know of have been found in this image. And they're like little red dots. I don't know where they are, but they're like some little red dots. These are basically galaxies that where the light has taken 13 billion years to travel to us. And the reason they're red is because the universe has expanded roughly by a factor of 10 since their light was emitted, and this has stretched their light, if you stretch light, the wavelength of light, it becomes redder and redder. Okay. Okay, so those are our 3 lessons. So now we are ready. Now we are ready. 7,000 years ago. Okay, this is meant to scare you. Like, if I were in the room, I would be like running. As you guys know, who answered the quiz correctly, 14 billion years ago, or more exactly 13.8 billion years ago. And the next line is going to sound amazing from my voice. In a world before there were worlds, there was an unfertilized universe. And it's you know, this is it. It's too small to be cute. And so this is the universe before our universe was the universe. And so what I'm going to show, this is a time when we really don't know what things look like. Things probably look a lot more crazy than this. Like my imagination is there like a lot of broken beer bottles, but what you're gonna see is that the nice thing about our theory for the creation of the universe is that it doesn't depend on how many broken beer bottles there are. Like that doesn't matter. The universe looks the same in the end. And so most of us cosmologists are convinced happens is that there's some particle that we probably haven't created in the lab. This is some atomic particle. And so this is a simulation of what it does. And so this particle is just existing in the universe. And it turns out that this particle, if it has certain properties, the troughs in the simulation have the right properties to seed our universe. And what I mean by that is that those troughs in that simulation, the things are actually growing exponentially. And so for a human, we're all familiar. So a human, you know, like 3 weeks looks like an egg or whatever, and then it keeps growing. So this is for the universe you would not want in your tummy. So the universe, this is the beginning of time. After 10 to the minus 30 seconds, it's doubled in size. Then it's doubled in size again by 2 times 10 to the minus 30. Doubled in size again. Doubled in size again. And this happens 100 times. In fact, in our theory, for things to work, you need to take a 1 meter region and you need to stretch it to the size of the observable universe. And if you do that, it explains a lot of observations that we see. It's kind of amazing. And this is called inflation. And so if I quickly you can see that if I keep doubling this, even by like 10, this is going to be, you know, so much bigger than anything. If I do this 100 times, it's ridiculous. Okay. And so a miracle occurs, a real miracle, which is that if you let the universe grow in this way, then on really small scales, our universe, we don't really notice this, but like there are actually particles on really short timescales appearing in and out of the vacuum of space. They're just appearing and disappearing. This is quantum mechanics. And it's actually important for many things. It's important for like a lot of processes that this is actually happening. These particles, these quantum fluctuations, so sometimes there are more particles in one place in the universe, and there are more particles than in another place, but it's only on really, really small scales. But if you then cause the universe to expand so fast that these small fluctuations are actually stretched to every scale. And they should have certain properties. And we look up at the sky, as I'll show you in a second, and the sky, and we see that the universe, like the seeds of structure, are actually these quantum fluctuations. So we are descended from these quantum fluctuations from inflation. So this is the miracle of exponential growth. Okay. And so this is kind of my most complicated slide. But okay, so then we have this particle that caused the universe to expand exponentially, and then this particle, it goes into other particles, because our universe is way more complicated than a single particle. So it goes into other particles. This is called reheating. We don't know exactly when this happens. It happens early. It looks like this. and some of the things it goes to, like one thing it goes to is dark matter. Because there's a lot more matter in the universe than the matter that we're familiar with. One of those particles is created in the early universe, we think, and it's called dark matter. We just don't know what it is. Another thing it goes into is quarks eventually, and those quarks eventually become protons and neutrons. So this is and it goes into electrons. And one thing that we know happens in the early universe is that around 1 second in the universe, there were a lot more electrons than there are today. There were also a lot more quarks before a millionth of a second. There are actually 1 billion times more electrons, 1 billion times more quarks. But there were also anti-quarks, and this had to be the case. We have an observable that tells us that there were these positrons, these anti-electrons, and they annihilate and leave only 1 billionth of the electrons at the end, the ones that are actually in our universe. And so yada yada, the neutrons and protons, as you guys had on your quiz, they eventually form hot air balloons or balloons, and then eventually the electrons. Things are really hot, but when things get less hot, the electrons like to bind to things. They like to bind to the protons and the helium, and when this happens, the light is released. So this is the light. There was a lot of light. Just like radiation that was kind of trapped by all the electrons. The electrons then grab onto to nuclei, and the light is able to travel. And this leads to emission that we see. If we could see 1 centimeter wavelengths, then what we would see is and we see this with our telescopes, is that certain regions, when I look at the sky in certain directions, certain regions have a little bit more have a little bit more radiation from the Big Bang than other regions, but they all have kind of the same amount of radiation. And so this is what the sky would look like at a centimeter. Like if this were Seattle, like if I looked up above Seattle and I could see at a centimeter, I would see that some regions have more stuff than others. And this is the light that's been traveling to us for 14 billion years from this time when it was released by the electrons. And so in particular, so what I was showing here is if I were looking at just a small patch of the sky, this is the whole sky. And so just like the Earth is a sphere, the sky I can think of as a sphere. And just like I can make a map where this is like North America and South America and Europe and Asia, I can do the same for the sky. And so this is the sonogram of our beautiful, almost baby universe. And I'm a cosmologist, which is a special type of doctor. And so I can look at this sonogram and I can tell that in 14 billion years, this universe, which is doing fine, is going to have an astronomy on tap. Okay. But this sonogram, things are kind of boring. These are actually part in 10,000 fluctuations. These are just small fluctuations in the universe that we're seeing. Like look at different directions, I just see a little bit more radiation, which means there's a little bit more stuff in one region than another. And so what the next thing that happens is that there's gravity. And gravity makes things, when there's more stuff in some location, gravity makes it amplify. Like I like to fall to the earth. Like stuff gets denser and denser. And so eventually things get dense enough that interesting things happen. And so the first interesting things that happen are kind of around a couple 100 million years. It takes the universe a bit of time, and you start getting stars. And so this is a couple 100 million year old universe, so you start getting stars. This is the birth. And then, but then it turns out that our universe went through a pretty angry or turbulent adolescence. And so you form some stars, and then those stars go into galaxies, and then and when you get a lot of stars like to explode, and then they start blowing gas out of galaxies. And so in the past there was a lot more star formation than there is today, and so this is an actual simulation that people have run of what the couple billion year old universe looks like. And so, in fact, you can see this is a few billion year old, and you can see that So this is galaxies forming, and then when the galaxies form stars, the stars like to blow up, the big stars, and this and so the adolescence of our universe was a bit turbulent. And so this leads to the present. Whoops. And so the present, you look up at galaxies and they're not doing a whole lot. Our galaxy is kind of boring. It's not forming that many stars. There are these elliptical galaxies, like in your question, that basically aren't forming any stars. And so like our universe has kind of settled down. You know, it's boring now. But wait. Oh no! It has a tumor. And so what we realized is recently, this is what we expected. This is healthy universe. Me as cosmologists look good. Our universe is not healthy. Our universe is growing very, very quickly. Galaxies are getting very, very far away from each other. Actually, most galaxies in the future, we're not even going to be able to see them. They're going to just move away from us too fast. They'll just disappear. And so this is not good. And so that brings me to the end. The end of the universe, the end of the story. And the end of the universe is cold, we think, and it's dilute and it's dark. Thank you. Questions? Yes.
Sorry, you mentioned like 14 billion years ago.
Yeah.
Sorry, I'm not really good at this topic, but is it fair to say the universe started like how big if we could imagine it like started?
Yeah. So the how big the universe is a question that we have trouble answering. So all that we can see is that we can see today that the universe is we can see things that are 14 billion light years away in essence. The universe is expanding, so it's a little more complicated than that. But and we can see that things look the same there as here. That maybe we're looking back in time a little bit because the light's been traveling. And so we know that the universe is a lot bigger than what we can see. And in fact, from studying things like the sonogram, which is the cosmic microwave background, we can tell that the universe probably has to be uniform on a much larger scale than what we're able to see. And in fact, this process of inflation, it would be surprising. Although there are theories that do this, it would be surprising if the universe were just kind of as far as we could see. So probably things are way bigger, but we can only see as far as light will travel.
In your opinion, what's the best theory for explaining dark energy?
Okay, so the question is, in my opinion, what is the best theory for explaining dark energy? And so there's a standard answer to this, which is that it's the energy of the vacuum of space-time. It's the same vacuum I was talking about, where things are appearing in and out. And so in this theory, that we can, with quantum mechanics, we can calculate the energy of the vacuum of space-time, and we make a prediction, and it's way big. It's 120. It's 10 to the 120th power off. So then how we explain this, especially this is how the string theorists like to explain it, is that that you can actually have the amount of energy in the vacuum fluctuate from place to place. And so imagine the universe is just way, way bigger than anything we know. There are certain regions where this vacuum has a much higher density, and there are certain regions like ours that are very improbable but have a low vacuum density. And then you could say, okay, then why are we existing in this region where the vacuum energy density is so improbably low? And so you can calculate and you can find that actually structures will not form in a universe where the vacuum energy is much higher than our part of the universe. And so this means that maybe we are only living in this huge multiverse, but we can only live in one part of it because the vacuum energy is low enough that we can live here. And that's called Anthropic Reasoning. Some physicists totally hate that. Actually, the last time I gave a talk here, it was on the multiverse. But the other theory is that it's like this, similar to inflation, that you just have some particle, and this is called quintessence. What people might criticize that theory in that it's even the tuning might even be more extreme than you need for the cosmological constant. To have a particle at today, it's very natural to have a particle in the early universe when the energies are high, cause the universe to expand a lot. It's much harder to have it happen today. Although this is also something that's gotten really interesting because the string theorists have come up with arguments that maybe it is a particle, but I won't get into this. This is getting too technical. But yeah, so this is something that people are thinking a lot of. Actually, many people think of this as the biggest difficulty with current modern physics, or the thing we understand the least.
So you're not a string theorist?
I'm not a string theorist. No, I'm a cosmologist. Yeah.
What questions do you like to see answered most in your lifetime?
What question would I like to see answered the most in my lifetime? That's a really hard question. There are questions that seem easier to answer. So I think answering what the dark matter is something that is more likely for us to answer than what the cosmological constant is. But the other one might be more deep. I think something that we might understand this inflation a little bit better. We don't know what particle is doing it, and so we might be able to say things about this multiverse, like what the structure of things look like before inflation. I think that would be really cool.
I got a two-parter.
Yeah.
News article recently said something about a fifth elemental force. Is that just clickbait? The second part of that, if it's not, how does that tie into dark matter and expansion and all the things we're trying to answer?
Yeah, so I can't. So the question is, he saw something about a fifth force, and is it clickbait or is it not? And I think it depends on exactly what the content was. But it is the case. So what are forces? So forces are different particles being exchanged between other things. Like electromagnetic force is photons that are going are causing an electron and a proton to attract. And so there are other particles in the universe, probably. But it's hard for there to be particles that are light enough that we haven't produced them in the lab for them to create a long-range force. So the answer is probably there's nothing important. Like the forces that we don't know are really weak forces that aren't relevant for anything. For you guys. Like for physicists, it's really cool. If you find some other force carrier, it is telling you about the fundamental physics, the fundamental theory of everything, kind of it's a clue into the structure of the universe. But it is very unlikely that there's a force a new force to find that's important. If there is a new force, it would probably have to happen for the dark matter, because we aren't made of dark matter, so it's very hard, or the dark energy to you could have forces that don't interact with us, and then it would be easier for them to exist.
Will the universe ever stop creating new stars?
Yeah, so that's a good question, and that's actually why I said it's a cold, dilute, dark end. Is that the lifetime for the sun, it's going to be around for 5-ish billion more years. And Jim, I'm sure, could probably correct me on the significant digits, but and there are other stars that will live longer, but they will all eventually run out of fuel. And some stars are forming, but the formation of stars is slowing down partly because of dark energy, and so less stuff is falling onto galaxies. You need gas to fall onto galaxies and funnel to the center to make stars. And so in 100 billion years, there will be very few stars in the universe. So the universe will start turning off. And so in the distant, this is probably not the first thing we should be worrying about, but in the distant future, the universe as we understand things, and this understanding does hinge a lot on our understanding of dark energy. But in our current picture, the future of the universe is pretty dark. And I guess that's also the current situation of the universe, or of the planet. Might not be too much better. Groans.
Any graphic of the universe with all of its galaxies, the galaxies aren't distributed evenly. They look like a two-dimensional spider's web.
Yeah.
Is there any theory about why the galaxies form like that versus having all the galaxies distributed?
So it actually fits really nicely with this inflation. So you get these quantum mechanical fluctuations that turn out to have very specific properties. And so the spectrum of these, or exactly where galaxies form, we have amazing models that are very accurate for predicting kind of that. And so this web, you start off with these fluctuations that were from this very early time, and they grow via gravity. And the reason it looks like a web is this is a little bit harder to explain to lay audience, but okay, I'm not even going to try to explain, but it's basically it's because if you know what a tide is, like the moon, pulls on one side of the Earth more than the other side, and this causes tides on the Earth. The same thing happens with where you have huge tidal fields in the universe, and it turns out that if you work out the mathematics, and it's not that complicated, you get this filamentary structure, which is called the cosmic web. Any other questions? Yes.
Is it generally understood that the quote-unquote end is when everything goes out?
Well, for me as a cosmologist, yeah, all stars going out would be one end, but so it depends, how imaginative you are. So that's not the last thing that happens in the universe. So there are still things in the universe. They're like black holes. Often people do quote the end as the black holes do evaporate too, and so that takes a lot longer, especially for like black holes of the masses in our universe. And so the end, actually, the expectation is if you wait long enough, you just have a bunch of particles floating around in the universe. And then there's a paradox. For me, this is like a ridiculous paradox, but I have a bunch of particles floating around for the end, for the rest of time. And so there's some chance that they will coalesce together and become a human. And so the paradox is that then you have a lot of time in the future. And this is called the Boltzmann brain paradox, or they become a human brain, and so you'd have consciousness. And so the claim is that might be the most prevalent life. Then maybe those are the universes where I should be saying that life exists. That's the condition on life, but then it's I don't know. Maybe that said too much, but yeah. So maybe this means that we're paid. We're funded too much. I should never say that, but because definitely these are things that people think about.
Since the inflation seems to be getting bigger, faster, more inflation going on, will it eventually, does that inflation flatten out with that curve? So
yeah.
Does it eventually flatten out? How much inflation does inflation continue?
Yeah. So this is a good question. So the question is, does inflation end, or does it? And so we know that inflation has to end because we exist. And so the inflation particle has to go into other particles and seed the universe. And so then but that's not the only thing. There's a reason. This is not the only reason our existence that we know that inflation ends. So we can look at the cosmic microwave background and we can make predictions exactly. If inflation ends, it has to start decelerating at the end. Like it can't always be exponential. And so we can predict what that should look like in things like this sonogram, the cosmic microwave background, and we see it. We see the inflation ending in the way it would if this theory is right. And so this is also something that makes us think very much that we have a good idea for this creation. Which is so this, in my opinion, this is the most ridiculous theory that we have. That we have a theory for what happens in the universe when it was like 10 to the minus 30 seconds old. We actually don't know too much for a while after that. But it turns out that how this theory works, it's very robust. And so we have a theory that has a lot of things that we can observe, and they've all checked out. This I find super profound. Done? Or there's one more question? Okay, one more. Okay, last question.
Yeah, so if everything is kind of fading out to kind of a cold, dilute darken, where does that energy go? Because if I just Newton's laws, we should assume that it's just converted, but where does that go if everything is kind of, it sounds like it's unenergized at the end of all this. So.
Yeah, so this is a good question. Like, where does the energy go? And I think a related question is just like, is energy conserved? Like I'm telling you, space is expanding, and the answer is yes. There's energy is conserved, and at the end, the energy is even though things are getting cold and dark, what is happening is there is light in the universe. It's come out of a bunch of stars and whatnot. And that light is around. It's just getting stretched. It gets stretched as the universe expands, and that's totally consistent with conservation of energy, because its stretching actually slows down the expansion of the universe, and so that's where the conservation is happening. And so it's getting the light, and when it gets stretched, that means there's less energy in the light, and it's looking colder and colder. So in order for me to see the light from stars, I would no longer be able to see it with my eyes because my eyes can only see certain wavelengths of light, and so it'll get stretched to wavelengths that are just the energies are too low to excite, like electrons in my eyes that I can see, and so things, it just fades away in a consistent way, but energy is totally conserved. Okay, thank you.